So first we're going to start off with kinematics without calculus. And for that we're going to start off with what the equations are. So if your basic one, we're about relating velocity from its initial velocity in terms of acceleration and time. You also have velocity relating to distance and time. Then you have distance relating to velocity, time, and acceleration. And finally, relating distance in terms of initial and final velocity without time.
Okay, so we have these four basic equations over here without calculus, but when you want to do kinematics with calculus, you basically have to partition up each of the position or the velocity into very small intervals, and that would make it v equals dx over dt instead of delta x. And then now the acceleration would become dv dt because you're partitioning the velocities into many small segments. So you can just rewrite all of these equations by replacing the a's with dv dt. And also, because in most of our problems we don't really use kinematics with calculus, we'll mainly be focusing on just the kinematics without calculus. Yeah.
We just want to take a quick look at the calculus behind kinematics by taking a look at their associated graphs. So if you start out with your position with the equation of 4t squared, so it's a quadratic that grows exponentially, you get a curve like that. Now we know that velocity is the derivative of position and acceleration is the derivative of velocity, but how does that affect, how do the graphs and the equations relate? So if you were to take the derivative of the position function, you get dx dt equals 8t. So this is equal to your velocity. Now that's a linear equation, which is shown by the graph over there. Now if you were to take the derivative of the velocity equation, which gives you acceleration, so this is the second derivative. You get a constant, which is shown by the horizontal line in the acceleration graph.
Alright, so given the previous example that we just went over, that the position is 4t squared and the velocity is 8t, which is the derivative of this, and the acceleration is the derivative of the 8t, which is 8. You can also do the inverse functions if you have acceleration or if you have velocity and you want to try to find the position. So you do that by taking the integral this time. So now if you have acceleration, that would also be equal to dv dt. And so if you want to find velocity from this, you need to take the integral of both sides. So now just switching the sides, you get velocity equals the integral of acceleration. And now you just set your upper, and it would be dt because you're going by time. And so now you just set your upper and lower limits based off of where you want to start and where you want to end. So if you want to start at some arbitrary t sub o and then end at some arbitrary t, then that would be your integral. And then you can do the same thing for position. It's just you need to take the integral of velocity this time because velocity equals dx dt. And you take the integral of both sides now, and then now you get position equals the integral of some arbitrary t sub o to some arbitrary t of
So we're going to take a look at a kinematics problem in one dimension. So the problem states that there's a car moving at 27.8 meters per second, and it decelerates to 0 meters per second, so to rest, in 17 meters, and we've been asked to find what the deceleration is. So we need to take a look at what variables we have, and that's initial velocity, final velocity, distance, and that's it. So in order to determine the acceleration, we want to pick an equation that has all three of those, the three variables that we have. So we can't pick anything that has time because we don't know what time is, and that would leave us with two unknown variables instead of just one. So the equation I'm going to use to solve is v final squared equals v initial squared plus 2ax. So our final velocity is 0, and our initial velocity is what's up over there. So we want to solve in order to determine what the acceleration would be. So you set acceleration, you solve for acceleration, and when you would solve out the problem, you would eventually get A to be 22.7 meters per second squared.
Alright, so now I'm just going to do some basic vector addition and subtraction. So if you have some arbitrary vector u over here that's facing up and to the right like that, and an arbitrary vector here, v, that's just facing directly to the right, you always want to line up the two vectors head to tail when you're doing addition. So you have vector v like that, and then you would take the tail end of vector u and put it outwards like that. And when you're doing addition, if you're doing v plus u or u plus v, it's commutative, so it doesn't matter, then your resultant vector will be like that, from this tail to that head. And this would be your resultant vector, u plus this one right there. And now if you want to do vector subtraction, it's the same thing as addition, but you would take one of the vectors and make it negative. So let's say you want to do vector u minus vector v, you would actually make vector v face that way to the left, and then you would just do the same thing as vector addition. So you have head to tail like that, and then you would have vector u right there, and therefore your resultant vector would be over here, u minus v.
So now we're going to take a look at a projectile motion and motion in a 2D problem. So here we have a person who is shot at an initial velocity at an angle of 30 degrees. That initial velocity is 26 degrees. So in order to solve this problem, we first want to break the velocity into its x and y components. So if you have your velocity vector going this way, you have your x velocity and you have your y velocity. And this is your angle over here. So in order to determine what this value is, it's adjacent to the angle, so the velocity in the x direction is going to be the initial velocity times sine of 30, or sorry, cosine. Cosine. And the velocity initial in the y direction is going to be v sub o sine of 30. So when you plug in 26 for the initial velocity in both cases, the initial velocity in the x direction turns out to be 22.5 meters per second, and in the y direction it turns out to be 13 meters per second. So the common factor between the x and y is time, and we actually have more information about the vertical because we know that on Earth, acceleration due to gravity is negative 9.8 meters per second squared. So right now in the vertical we have information about three variables. Initial velocity, which is 13 from what we determined, 0 at the top point because that's when the force of gravity overcomes the initial velocity, and the acceleration itself. So using these three equations, we want to find what the value of time is, because that's how long it's going to take for it to go up to that point. And then since the distance time to go up and time to come down is the same, we can just multiply that by 2. So the equation we want to use in order to determine time, because we have initial and final velocity and acceleration, is v final equals v initial plus at. So plugging in our final velocity, which is 0, and our initial velocity, which is 13, you can solve this equation to get t equal to 1.33 seconds. Now that's only the time to get to the top point of this projectile motion. So we need to have 2t in order to determine the total time that it takes to get from point A over here to point B, which is going to be 2.66 seconds. So now that we have the time over here, we're going to determine what the horizontal distance is. So in this case, what we have is the initial velocity in the x direction, and the time that it takes for that entire projectile motion to be covered. So the reason we only need one velocity and not two like in the other case is because there's no acceleration in the horizontal direction, nothing acting upon the person to stop him from moving in the horizontal direction. So the equation that we're going to use is v equals delta x over t. So solving for delta x, you get delta x equals v times t equals the velocity times the time. And when you multiply that, you get 59.6 as your final answer as to how far that person moves